Hello and welcome back to Mr. Powers Teaches Algebra 2. Okay, so what's going on? Well, we've been talking a lot about rational roots. And we've been talking about, no we haven't, not rational roots, but roots. We've been finding lots of roots. I'm finding zeros of polynomials and sketching polynomials. We've been looking at zeros and their multiplicity and all these things. But we're going to keep going, and now we're going to go over the rational roots theorem pretty much. And that tells us, with certain polynomials, what all the possible rational roots can be for a polynomial. And because we can do that now, we will be able to factor much larger polynomials than we have been able to up till now. And not in a factor, but we can find more zeros as well. So anyway, let's go ahead and take a look at these, and you'll see what I mean. Okay, so rational roots theorem, it can also be called the rational zero theorem. I stole this from QMath, and well, without further ado, let's read it. The rational zero, or rational root theorem, states that each rational zero of a polynomial with integer coefficients f of x equals a sub n times x to the n, a sub n minus 1, x to the n minus 1 plus ... plus a sub 2x squared plus a sub 1x plus a naught is of the form p over q, where p is a factor of the constant a naught. So in other words, p divides this right here, and q is a factor of the leading coefficient a sub n. So q will divide that. P and q are relatively prime as well. And so what does that mean? It means that p over q, if it is a possible rational root, it will be in its simplest form. It will be a reduced fraction. Okay. It's a very neat theorem. If anyone is interested in me proving it, there are other proofs out there, and it is a pretty easy proof to get, I think. Let me know, and I'll be happy to make it. But for now, we're going to use it. Here's another way to state that also. Now you can see QMath right here. So I grabbed this from them. A rational root of a polynomial function. So if the function is in this form here, I won't read it again, then a rational root will be of the form p over q, where p is a factor of the last term, the constant, and q is a factor of the leading coefficient. And something we got to note is that all the coefficients in our polynomial are integers. Otherwise, this little theorem doesn't work. So that is a requirement of this guy. Okay. Now we've gone over it. Let's go ahead and talk about what our process for finding these will be, and then we shall find some. We'll go through one example, and then we'll maybe do another one. So what's the process? Use a rational root theorem to list all possible rational roots. And then what? Well, use synthetic division to factor out the factor that corresponds with that root, and keep going. Do it again. Do it over and over again until we have our polynomial factored all the way and we find all our roots. It's very, very simple, but here it is. So now that we've gone over all of that, let's do an example. And I'm a little hesitant because I know it's going to be long. So this video is already 4.5 minutes. But let's go ahead and take a look at this example. So determine all the zeros of p of x equals x to the fourth minus 7x cubed plus 17x squared minus 17x plus 6. Okay, so first things first, let's find our p's, possible p's. P can be any factor of our constant, right? Because remember, we want to find all our p over q's, all our possible rational roots, and those are going to be determining by p and q. Well, p divides our constant. So what are the factors of 6? Well, that's easy. 1 divides everything, and of course we're going to go plus or minus. 2 divides 6. 3 divides 6. And, of course, 6 divides 6. And those are all our factors. Q, all our possible Q's, the nice thing about this one is our leading coefficient is a 1. So, what divides 1? Well, 1 divides 1. So plus or minus 1 are our factors for Q. So what's our P over Q's? What are all those? Well, it could be 1 over 1, which is 1. It could be 2 over 1, which is 2. 3 over 1, which is 3. So we got plus or minus 3. And 6 over 1, which is 6. Plus or minus 6. There's our list of all our possible rational roots. It's a very powerful, really fun theorem. So if there are rational roots, this is all of them. There's 2, 4, 6, 8. 8 possible. Now, could there be irrational roots? Sure. Absolutely. And if they're all irrational roots, we're not gonna be able to do anything. So let's see if we can. I mean, we're told to find this, so yes, this will have rational roots. At least a couple. Okay. Because if there's 2 that aren't rational, that's okay, because we can do anything that's a quadratic. So you'll see what I mean here in a second. So now we got to start testing. So let's try, I think I want to try -1 is what I want to try. So let's see if -1 will divide it. And the way I'm going to do it is I'm going to use synthetic division. So let's go ahead with the synthetic division. We'll go ahead, is -1 a 0? In other words, x plus 1, is that a root? All right, and then we got 1, -7, 17, -17, and 6. Those are our coefficients. Let's do the synthetic division here. Okay, bring down the 1. 1 times -1 is -1. Add it, we get -8. -8 times -1 is 8. Add it, we get 25. 25 times -1 is -25. Add, we get -42. -42 times -1 is 42. 42 plus 6 is 48. That it would be our remainder. So in other words, if I divided our p of x by x plus 1, I'd get a remainder of 48, which means it's not a factor. All right. Now, another way I could have checked is I could have just plugged -1 in to our p of x. I could have found p of -1, and I could have checked, is that equal to 0? And sometimes that's pretty quick. But what if I'm plugging in a 6? P of 6, oh, well then 6 to the 4th, 6 cubed, 6 squared. Those are big numbers, hassle. This process, generally speaking, is going to be pretty quick and easy. So I'm going to go with the synthetic division. -1 didn't do it. Let's try 1. Let's try 1. So we're going to plug in our coefficients again. 1, -7, 17, -17, and 6. We're going to bring down this one here and go for it. 1 times 1 is 1. The 1 here, add it, we get -6. -6 times 1 is negative 6. Add, we get 11. 11 times 1 is 11. Add, we get negative 6. Oh, it's beautiful. Negative 6 times 1 is negative 6. Add, we get 0. That is exactly what I wanted. So now we know that 1 is a root. And we know what we end up with. So now let's go ahead and rewrite p of x. Excuse me. Okay, so now I have, because of this guy, we know that p of x can be rewritten as x minus 1 times 1x. Well, wait, what do we have before? We had x to the 4th. So now we're on x cubed. So 1x cubed minus 6x plus 11x. Oh, I'm sorry. It would be x cubed minus 6x squared plus 11x minus 6. So we are one step closer. We found a 0 at 1, and we are one step closer to getting this guy completely factored in, to finding all our zeros. All right, so let's keep going. Now we found out negative 1 is not a root. We found 1 is, but there could be multiplicity of 2. In other words, 1 could be a root twice. So let's try to divide 1 into it again, into what's left right here. Let's divide this by x minus 1 and see what happens. So I'm going to try it again, put a 1 there, set up my synthetic division, and we're going to get, let's see, 1x cubed minus 6x squared plus 11x minus 6. Okay, let's go. Bring this one down. Here, let's change it. Right there. Okay, 1 times 1 is 1. Plus 1, add. We get negative 5. Negative 5 times 1 is negative 5. Add. I get 6. Oh, it's beautiful. 6 times 1 is 6. Add. We get 0. It did work again. Oh, you love to see it. It's almost like I have worked this out before and know exactly what's going to happen. All right. So anyway, p of x equals, so now I get, well, I'll factor out an x minus 1 again. I'll just write x minus 1 squared times, well, we divided x cubed by x minus 1, so now I got x squared. So it's x squared minus 5x plus 6. There we go, just taking these coefficients here, throwing them right here. Okay. All right, now we got one more thing to do. Well, no, we can keep going, but you know what? Once we're done, once we're down to a quadratic, we're good to go. We know how to solve quadratics, any quadratic. We can solve any quadratic, and we like to do it by factoring if we can. And I'm looking at this guy, and I can see, yeah, it's definitely factors. So I already know. I'm just going to keep this going. I have my x minus 1 squared. And this guy factors to x minus 2 times x minus 3. That's old stuff. Easy. So now I know all my roots and the nature of each root. We got a root at x equals 1 with multiplicity 2. We got a root at x equals 2. Multiplicity 1, and a root at x equals 3, multiplicity 1. 3 roots, 1 came up twice. So you'll love to see it. It's beautiful. So that'll do it for this video. Nice 15-minute video for you all. And so these problems are a little lengthy. And this was actually a nicer problem. So may do another problem for your benefit here, but that's later. Until next time, enjoy doing math.